so the last thing we're going to talk about is application. So again, we've done most of the major rules. We'll have a couple more rules in chapter 2 when we get there. But most of the major rules for derivatives we've talked about. All right, now we're just going to apply them. Look at applications. So a couple simple applications. All right, so first, suppose this is a cost function. So C of x represents the cost in thousands. So I got to remember it's in thousands of dollars. To produce X airplanes, find the rate at which cost is changing when 20 airplanes have been produced. And so what I want to find is the rate. Well, that means derivative when production level X is 20 airplanes. All right, and then I got to be careful with always include units and kind of give your answer as a statement, right? It's an application. Your answers have context, so make sure you include the context. The derivative first, though, this is a complex derivative. It's going to require my product, not my product rule. It's going to require my chain rule. Right, the 200 out front just comes along, so that 200 comes along. 2,000, not 200. Then it's the chain rule. The power outside is 1/3, so I pull my 1/3 out to the front, leave the inside alone, raise it to negative 2/3, right? 1/3 minus 1 is negative 2/3. Not done yet. Remember, that's just the outside. I have to then times the derivative of the inside. So the derivative of x squared plus 2 is 2x. I've got to remember to times 2x. And then the 700 will just zero out. All right, now you could technically leave it because I'm just going to plug 20 into it. I'm going to clean it up a little bit. I'm going to multiply the 2x and the constant. Now I'm going to leave the fraction because I don't want any approximate answers till the end. So it'll be 4,000 over 3 times x squared plus 2 raised to the negative 2/3. All right, then just be careful when you type it in. Right, when you type your 20 in, my rule of thumb is always more parentheses. So, again, I would just go and put parentheses kind of around everything. My biggest thing is make sure this fraction up here is a negative 2/3 all up in the exponent when you raise this. All right, then multiply that out and just do it very carefully, and it should come out to be 489.5736 if I round a few decimal places. And remember, that's in thousands of dollars per airplane, right? Because this represents the change in cost with respect to the change in x. X represents airplanes. And so it's the change in cost. Cost is in thousands of dollars. So change in cost in thousands per change in x. So x represents number of airplanes produced, and per airplane. So the how you kind of write that answer out as a statement. So when production is at 20 airplanes, and it is important that it's at 20. If I was at 30 airplanes, I'd have a different rate of change. 10 airplanes, I'd have a different. So it's that specific 20, right? When they're at 20 airplanes being produced, the cost is increasing by, you can either write out the word 1,000, or you can multiply this number by 1,000. That's probably what I would do. I would do dollars, right? Dollar sign. And I'm going to just write this in terms of 1,000. 489,573.6 per airplane. I'm going to fit that in. Per airplane. Alright, so that's how much it's increasing. So that's the rate, the cost. So our cost is going up that fast, at that speed, when production level's at 20. Production level's at 10, it would be a different speed. Which actually in the next example is what we're going to look at, kind of compare two different speeds. Alright, so the next example is so that was a business example. This is more of a social example because it's population, social science. Alright, so the function p of t, which is 2,000 t divided by 4t plus 75, gives the population of deer in an area after t months. So time is in months. A, find the first and second derivative. B, find the value of the first and second derivative at 10, 50, and 100. Right, and then interpret the meaning of B. Right, what's happening in the long run. Right, so first the derivatives. Sorry, so the hard part. So this is going to require my quotient rule because it's a quotient. That's it. Just the quotient rule for the first derivative. Alright, so I'm going to find my first derivative. And then I find my second derivative. Alright, so it's the low times the derivative of the high, which is 2,000, right? Because it's 2,000t. 2,000 comes along, derivative of t is 1, minus the high, 2,000t, times the derivative of the low, which is just 4, all over the low squared. All right, then I'm going to simplify that because I'm going to use it to find my second derivative. So up top, multiply, so this is going to multiply out to 8,000t plus 15, 150,000, 4 zeros after that, and that's minus 8,000. Alright, so the 8,000's cancel out, and I'm still going to leave that over. I'm not going to square that out. Alright, I think it's just easy to leave it. It's up to you. You can square it out if you want to. If you square it out, then you don't have to use the product rule. Or, not the product rule. You don't have to use the chain rule. Alright, but I'm going to leave it because I think it's just good to practice. Alright, so up top, I just have that 150,000 divided by 4t plus 75 squared, the whole group squared. Alright, so there's my first derivative. Alright, first derivative. Now the second derivative. So derivative 2. Again, I'm going to leave it, so I'm going to have to use the quotient and the chain, so it's the low, times the derivative of the high, and I'm going to do that because what's the high function? The high function is just that really big constant. What's the derivative of a really big constant? Well, that's just going to zero away, so that whole thing's going to zero out. Then it's minus that top function, which again is just that constant. Derivative of the low is going to require the chain rule. I pull the 2 out. 4t plus 75 raised to the first. Not done yet. Still got to multiply by 4, right? Because the derivative of the inside is 4. All over the low function squared again. So you could just write that to the fourth if you wanted to. Alright, so up top, that's gone. I have I believe that's what that multiplies out. So I've got my 150,000 times 2 times 4. 1, 2, 3, 4, 5 zeros. Make sure I get enough zeros. 4t plus 75 all over 4t plus 75 to the fourth, and then I can reduce one of those. And so the final simplified answer, now when I did the complete your notes, I actually did this derivative a little different, because I think it's just good to show you a couple different ways. Alright, but that's using the quotient rule. I got all my zeros there, and there's my second derivative. Alright, so my first derivative and my second derivative. Alright, now we're going to use it. So part B, find both at x equals 10, 50, and 100. And then we're going to kind of see what's happening there. So I'm going to find my derivative at 10, find my derivative at 50, find my derivative at 100. So again, I'm going to plug them back into my first derivative and then my second. I'm going to plug them back in here. And so what I would probably do is I'd actually graph that and then just hit the value key. Alright, since you got to plug in 3 different values. And I'm just going to give them to you. You guys can check them out on your own. Alright, so when I plug 10 in, I get 11.34. When I plug 50 in, I get 1.983. And when I plug 100 in, I get 0.663. And remember what this means. Alright, it was the population of deer after T months. Alright, so this was the population of deer. The deer was increasing by deer per month. Alright, so that's the population was going up by about 11 deer per month. Then after 50 months, it slowed down to almost 2 deer per month, and then it's less than 1. Alright, so kind of keep that in mind because the last question was to interpret it. Alright, so there's the first derivative. And so the rates of change were decreasing. You're still adding deer, but you're adding at slower and slower and slower rates. Alright, and so it should be deceleration. My second derivative's based on that, I believe, should come out negative. So now my second derivative at the same values. And so again, what I would probably do is graph my second derivative and then use the value key. Or you just plug the numbers in. So remember the second derivative, so I'm plugging these into this one. Right? And again, actually based on this number here, I know it should come out. And it should, because my rates of change were decreasing. So I'm decelerating. So my derivatives are getting smaller, ergo the second derivative should be negative to represent that decreasing. Right. Again, I'm going to give them to you. You can check them out on your own. They are all negative and small numbers. So this is a negative 0.789. This was a negative 0.0577. Negative 0.0112. And so deer per month squared, right? Would be the acceleration is the change in my function per my unit squared. All right, so it's decreasing by, negative means decreasing. The rate is moving down by 0.789 deer per month squared. And so it's decelerating, it's slowing down, and it shows that, right? My values were getting smaller up here, my rate of change were getting smaller. And so you can interpret that however you want. Now I'll probably pop up, or at least show you what the graph of the function is so you can kind of see that's what's happening. All right, so see, the rate of change in the deer population is increasing, right? It was always moving up, but, right, because they're all positive, but at slower rates every month. Because the second derivative was negative, the rates were decreasing. They're still positive, so I'm still adding deer, but I'm adding deer at a slower and slower rate every month. Right, that's what's going on here. So decreasing rates. And you can kind of see that if you graph the original function. So I'm just going to pop it up here. You can graph it on your own calculator if you want to. So I'm going to graph the original P of t function, which was 2000t divided by 4t plus 75. All right, now I'm going to just graph it in a window where our numbers kind of, right, where deer population should be positive, time should be positive. And so I'm going to let my x max, right, I want to make sure I go out to 100, so I'll probably do my x max 150, my x min, I might just do -2 so I can see my axes, my y max, you know, I probably don't need to go real big because, again, 11 was what it was with my derivative. Oh, but it's the deer population, so I might have to go fairly big. I'll go 1,000. And then my y min, maybe -2 so I can see my axes. Alright, so I'm going to start with that window, and I may still have to adjust it from there. So I'm just going to graph it on my calculator, and then I'm going to pop it up. Oh, and this looks like a perfectly fine window. Alright, so my x value is my time in months. This is my deer in my population. Alright, starts off, if you plug 0 in, you get 0 out, right? If you plug 0 in, that zeroes away. And then it's got a slight curve to it. Alright, so it's curved like this. There's my population of deer. And so what is happening is it is leveling off, right? It is slowing down. So it first starts off growing fast. So it grows fast. But then it slows down, right? My slopes are getting slower. So it slows down and actually approaches a 0 slope. It's kind of flattening out. And it should make sense. Populations do that, right? You run out of space and food, so eventually the growth has to slow down due to lack of resources, right? You can't fit any more deer in this particular region, and so they slow down, and the growth, you still have no deer, but the growth slows down to a bare minimum, to a very small value, all right? Approaches almost 0. All right, and so that's the rate of change and the acceleration. All right, so we'll stop there. So we're all done. Chapter 1. All right, so make sure you go over practice the derivative, practice finding, practice all your rules to get ready for the exam.